A factory produces yellow tennis balls and white tennis balls. Independent samples, one of yellow tennis balls and one of white tennis balls, are taken. The table shows information about the weights of the yellow tennis balls, Y grams, and the weights of the white tennis balls, W grams. And we can see all of that in the table. In part A, we want to find a 95% confidence interval for the mean weight of the yellow tennis balls. So we're working just with the yellow balls here. So it's a 95% confidence interval. So we want the value of Z95, which we can find from our tables, and very often just from your calculator, as 1.96. Then the confidence interval is, we can see the mean for the yellow balls is 57.2. Take away that Z value multiplied by the standard deviation for the sample, which will be 1.2, which is the population standard deviation, divided by the square root of n. And we can see the sample size here is 120. And then the upper end will be 57.2 plus 1.96 times 1.2 over the square root of 120. And then it's just a case of calculating that. We get 56.985 and 57.415. Jamie claims that the mean weight of the population of yellow tennis balls is greater than the mean weight of the population of white tennis balls. A test of Jamie's claim is carried out. In B part 1, we're asked to specify the approximate distribution of Y bar minus W bar under the null hypothesis of the test. Now, we're actually going to do the test down here in part C, but let's state the null and alternative hypotheses at this stage. The null hypothesis would be that there is no difference. So the mean for Y's is equal to the mean for W's. The alternative is Jamie's claim that the mean for the Y's is actually greater than the mean for the W's. So we're looking at Y bar minus W bar. That's going to be a normal distribution. And since the null hypothesis is that the means are equal, the difference would be 0 here. The variance is going to be the sum of the individual variances for samples. So that's going to be 1.2 squared. Remember that the variance is the square of the standard deviation, but we have to divide here by the number in the sample. And then for the white tennis balls, it's 0.9 squared over 140. So that's B part 1. Part 2 of B is to explain the relevance of the large sample sizes to your answer to part 1. The large sample size means that we can use the central limit theorem. So we do not need to know the actual distributions of Y and W to use the normal distribution. Now in part C, we're asked to complete the hypothesis test using a 5% level of significance. You should state your hypotheses and the value of the test statistic. Well, we already stated the hypotheses up here, but just to make sure I get the marks, I might restate them down there. And then we can go ahead with our test. Now it's going to be a one-tail test because we're just looking at whether mu y is actually bigger. And we know that we're using a normal model and 5% level, one-tail test. So we've got 5% down here. We can look up the correct Z value for that, and it is 1.6449. And now we need our test statistics. So I found this in the formula booklet, and our hypothesis is mu y is equal to mu w. So all of that just becomes 0 there. And so the calculation that we need to do is the mean for the yellow tennis balls, 57.2, take away the mean for the white tennis balls, which is 56.9, and we can see that what we have here is the square root of the variance from up here. So we can calculate that, and that is going to be 1.2 squared over 120 plus 0.9 squared over 140. Put that in the calculator and we get 2.249 as our test statistic. And we can see that 2.249 is greater than the Z value from here, 1.6449, which would put that value up here somewhere, so well and truly in the critical region. And so we can make a statement that we would reject H0 and we would say there is significant evidence to support Jamie's claim.